Okay, good morning everybody. So today we will work on forward kinematics. But first we want to extend our system to include to 3D, from 2D to 3D. So if you have a look at this here, we can now draw 2D shapes. We can translate them, rotate them, scale them, skew them. And this is all done using transformation matrices. So in the 2D case, it's a 3x3 matrix. If we move into 3D, then we're dealing with a 4x4 matrix. So now I already wrote some code to deal with 3 dimensions, and I will just make a copy of this notebook. We do them in 3D. So here is a set of functions that I use often when dealing with kinematics and humanoid robots. So I'll save that as JB geometry function. And here's a link to the Google Collaboratory that I'm working on right now. So now let me draw some other shape. And these ones we can delete. All the way to finalize. So if you look at this program here, there's two major changes. We import our matplotlib library. And my geometry file as JBG. And then here we import a new module, Axis 3D, which allows us to draw in 3 dimensions then. So now let's think of a shape that we can draw in 3 dimensions. Arrow is a little bit, we did that already. Let's just draw a block, a brick. So we have 2 walls. And now I need to specify the coordinates in 3 dimensions, x, y, and z. Here. But I also need to convert them into, later on I have to remember to convert them into homogeneous coordinates. So I need to have them as 4 entry row vectors or column vectors. So let's build a little house. We have a floor. Floor is from 0, 0, 0 to 1, 0, 0 to 1, 2, 0 to 0, 2, 0 to 0, 0, 0. And here I need to, I'm gonna add 1 extra function because it shows up relatively often. And np.ones length of the array. make that a little house. So we draw the floor. And now the first row is going to be our x coordinates. Second row is our y coordinates. And I use slicing for NumPy arrays here to just extract the rows that I need. So row 2 every entry. So now this is X, Y, and Z. Color is black. Draw it with this line style. Color is black. Actually, I could also just say it like this. I think line style is so now go call draw the house with the axis. Specify the color of the house and line width, sure. As arguments. Oops. So here now is my floor plan, right? That's the bottom of the house. You can see it's a rectangle in 3D. The range is not the same. Here is 0, 0, 0, and then this would be the x coordinate, y coordinate, and going up is the z coordinate. I want to specify so that it doesn't look skewed. I want to specify that the coordinates are equal. Oh, okay. From 0 to 2. Actually from -1 to 3, -1 to 3, and Z I can set from 0 to 3 to 4. So here's the rectangle of my house now with the axis -1 to 3. Is this 0 to 2? Y limit. So here's the basement of our house. Now I can do some tricks for plotting the roof, the ceiling. The ceiling is the same as the floor, it's just the Z coordinate is different, right? So I can change that, and now I can say that for every X, every Y coordinate, the 0, 1, 2, sorry. Row 2, every entry, instead of being 0, I now change it to the height of the house. Let's make the house 1.5 units tall. Then I can plot that again. How come I only have one now? Copy. Need to make a copy of this. C2. C2. So now we have the floor of the house and the ceiling of the house. Then we need to put in some walls. So we will do this as an exercise. Take this code and add the walls and a roof to the house. Okay. So you have to finish and submit within 15 minutes. So here, this part of the program, you want to add the calls so that it will draw the walls, and then so it will draw a little roof on top of the house, which is sort of a triangle. Now this is going to be a wireframe, so it's not a 3D computer animation project. So just to give you some experience with dealing with the Matplotlib 3D functions. So respond with yes if you understand the question. Otherwise I have to assume that you're just sleeping here. And I suggest you practice this. Take this opportunity now, because the midterm will be next weekend, and then I will ask you to write some more complicated programs. So the JB geometry file is this part here. So you can either just copy and paste that into your code, add a comment, JB geometry.py. Actually, let me do that differently. Here's the okay. Save as. On the desktop. Actually, I'm not using any function in JB Geometry at the moment, but here's the file. Since we will be using it later on. So here, let's see how we can draw the walls. So let's draw the wall at x equals 0 first. So we start at 0, 0, then x will remain 0, so we need to go to y being 2. Then we need to go to the height of the building, so that will be 0.2 point, and what did I set for the height of the thing? 1.5. Then we go to 0, 0, 1.5. And 0, 0, 0. There needs to be a list of lists. And I just change the color here first, make it green. JB And now we have a wall on the left hand side here, right? So then I can make a copy of it. Now I have to change the x coordinate of this wall to move it to 1 unit. Then draw it again. Now we have 2 walls, left and right, as you can see. So now the front is sort of drawn already, and back. So now let's say what the roof should be. So the roof, let's make it look a little bit more interesting. It should start at coordinate 0, 0, 1.5. That's where the ceiling is. Then from there we go to 0.5, 0.8, let's say, and z coordinate 1.7. Then from there we go to 1, 0, 1.5. Make it blue. See, so now we have a slanted back roof here. Y is 0.8, X, Y, Z. Yeah, a little bit higher. And then I have to plot the backside of the roof. Backside of the roof will start at 0, 2, 0.5, 1.2, 1.7, 1, 2, 1.5. And lastly, I need to have the connection line on the roof. And that would be from 0.5, 1.2, 1.7 to 0.5, be 0.8 here, 0.8, 0.5, 1.2, 1.7. And now you have our roof triangles here too. So now I also want to apply this as a homogeneous, being able to apply various affine transformations to it. So C is equal to A dot C, C2 is equal to A dot C. Actually, I don't think I need to actually copy that, right? C. T and T, our transformed coordinates. Then I take that roof and I also apply our transformed coordinates. T and T. So we have the wall. Okay, so let's see if that worked. So here's still our house. Now let me make the figure a little bit bigger. Right, okay, this is better, so easier to see. And then I want to put another house there. And what I want to do is I rotate the house by 40 degrees. And after that, I translate it 1 unit to the right, 0.5 backwards, and 0 in Z. Translate is not defined. What did I call it? Translate. Ah, yes. Oh, so color should be red, line width 1, and then A. So now we have 2 houses, but I want to move it to 3, I guess, so that they don't overlap, or I rotate it by -40. And I can scale the house. Let me make sure I actually defined that. I defined rotate, 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 translate, but I didn't define any scaling function, so that's okay, we can do that now. So first I make the house smaller. Uh, 0.5, 0.5, but I want it to be a little bit taller, so we'll make it 50% taller. Let me just define that function quickly here. That's because in Python you have to be careful if you use modules, then when you import it once and then you change the file, it is not actually going to reload the file. It caches the import. So every time you do an import here on JBG, as you saw, JB geometry, I added the scale function, but then when I tried to run it, it couldn't find scale function because it uses the old version of the module. So usually you have to, if it's something major, you have to restart your kernel restart your Python program, then everything will be fine. But I was a little bit too lazy, so I just defined it by hand. And then of course this one I have to, I can also use reload, I guess. No magic to do that. Okay. Fine. I just restart the runtime. Now you can see here we have two houses, the original one and then this one, which is not as half as wide, half as long, but 50% taller. And I can move that to a better place. Move it to 2. So there you can see, now we have 3D points that we can manipulate using rotation, scaling, and translation. And then of course I can have these things morph into any shape that I want to use. Now, why is that important? I think it's important for humanoid robotics because the next problem that we're discussing is the problem of kinematics, and there's two versions, the forward and the inverse kinematics problem. For that, being able to visualize and draw the coordinate systems is actually very important when you're trying to derive the kinematics of a complex robot such as a humanoid robot. It's very easy to get confused. So I think the matplotlib, being able to draw things quickly, is very helpful in trying to derive the kinematics of a humanoid robot. So let's have a look at the forward kinematics. I think that's the same thing. No, that's not what I wanted to show. add this to the 3D coordinate system thing. So here let's draw another figure from some other slide, a little spiral. The spiral I generate by modeling velocity and direction of the turn. So we start out with the current position 0, 0, 0, 1, because in homogeneous coordinates. Then we take a step in the direction of the angle and then increase the velocity so that we get bigger and bigger movements as we go up in Z. So our translation is cosine and sine and a constant dz for moving upwards. So if I plot this, then it will look like a spiral coming up like that here. So you can also do functions, animations like that. So let me fix this for the slides. A little bit smaller. And here's the output with our two houses. Let's make it a little bit smaller. 8 and 8. And then S2. here's the image of our spiral. That would be those, yes. And then here, we'll now create the forward kinematics. That notebook I can share with you is here. So this is the notebook for the forward kinematics. Let me update this one. Still running. Okay, done, done, and done. And then I want to delete those. Last one, finalize. So let's talk about the kinematics. So first of all, if I want to control the robot, if I want the robot to do what I tell it rather than to move around randomly or to behave in a completely random pattern, then I must know the effect of my control, right? I need to be able to predict what will happen if I change something. Now, for the control of the robot, in humanoid robots, we use most commonly Revolute joints, servo motors that can rotate in one direction. So here my arm, I can rotate the arm. This would be 1 degree of freedom, one motor that I can control, one revolute joint. So for example, the elbow or knee, um, so what I can actually control in this is the angle between the two links. So for example, with my elbow, I can set it to 90 degrees, 135 degrees, 45 degrees. For this joint here, I can control this angle. Now similarly in my shoulder, I can also control the angle from here to there, let's say. But shoulder is a more complex object because I can rotate it in two directions, two dimensions, in three dimensions actually. For shoulder, I can rotate it this way, I can rotate it this way, or I can rotate it this way. So more complex joints, which are called then rotational joints, I can model them as combinations of revolute joints. With common position. So for humans, the most complex one would be shoulder and hip, where we have 3 degrees of freedom combined. Now, for other kind of robots, there we may use prismatic joints, which are the kind of joints that instead of doing rotation, they move things along a straight line. So they move backwards and forwards. Humanoid robots, these kind of the motors that allow us to do this kind of motions are linear actuators. Which are then, if we use those, then this is called a prismatic joint, 1 degree of freedom, sliding, translating along a straight line. So now let's have a look at an image of a humanoid robot. Can put that in here, and we'll copy the Thormang robot. So here is the CAD drawing of one of the humanoid robots in my lab. It's a Robotis Thormang robot. It's our tallest, most complex humanoid robot. We do different robot sports and magic tricks with it. Let me just show you quickly one of them. I hope I have the video. No, I don't have the one I wanted. Let me check. Okay, I'll just look at this. So this is not the total robot. This is actually just the upper body. But here we programmed the robot to learn how to type on a keyboard. So this is our robot, just the upper body, and then it learns how to grab the keyboard. This is done actually using reinforcement learning. You can see here is a plot of our training as the robot is learning how to type. Here's the simulation that they're training with the robot, simulating what happens when it moves around the keyboard. He's typing now. Yeah, okay, now he's going to start typing. So this is again an exercise in manipulation of high accuracy manipulation. You have to be very precise if you want to hit the right key. But now you can see the robot is typing, "Welcome to the ERC lab." So if we want to implement this on the robot, you can see what I have is I want the robot to type these keys. And let's say we're not doing it with reinforcement learning, but we are actually programming the robot to hit the keys at different geometrical positions with the correct amount of force. Then I can figure out where the keys are, but my problem then is I need to move the fingers in such a way that the finger will actually touch the key, right? Hit the key. That particular problem is called the inverse kinematics problem. It is actually a more difficult problem, then the first problem, the forward kinematics problem, that we will discuss. Here we're typing. Wheel. Cannot use that video at the moment. How was Okay, now we have it. So then you can watch the video there. So when we look at that problem, if we don't do any learning, then we have to set the robot joint variables, the angles, so that the finger will reach the correct key. And that problem is called the inverse kinematics problem. Now the forward kinematics problem is given a set of joint variables, angles, calculate the position of the finger, or more generally the end effector. So in this case, that would be if I set the joint angle to 10 degrees, 12 degrees, 15 degrees, so on and so forth, then where will be the position of my finger? So both of those, of course, for a single joint, it would be very easy. I would just apply a homogeneous transformation matrix. And I can do rotation and translation, but now we need to worry about the cumulative effect, right? Because if I move this shoulder joint, then the elbow and the wrist are also going to move. So they are coupled, they're connected. This one up, this one down. So first we need to introduce the concept of a kinematic chain. So in principle, a robot consists of a set of joints that are connected by links. Each joint has 1 degree of freedom. If, like I said, we have shoulders with multiple degrees of freedom, then we would model that as 3 joints, in this case, that all share the same position but different axes of rotation. So So let's stick with US English. More complex joints are modeled as combinations of 1 degree of freedom joints with zero length between them. For Revolute joints, this would be the angle of rotation. For prismatic joints, this would be the displacement or translation. And again, to separate. So we need to worry about the cumulative effect of these joints. However, it's clear that if I am concerned about my right hand, the position of the end effector, whatever I do with my left hand is not going to have any impact. So the joint angles that I send on my left arm are not going to influence the position of the end effector of my right arm. Because of that, we group joints together. Joints that are connected together are grouped into kinematic chains, and then I need to break down the robotic system into its kinematic chains. So in this case, for humanoid robot, we usually have 5 kinematic chains. Just like for humans. left arm, the right arm, the left leg, the right leg, and the head. Head can also move. Pan, tilt, and sway. So there's 3 degrees of freedom in the head for humans. And you can see those in the kinematics of our Thormang, right? We have the head assembly, the left arm, the right arm, the left leg, and the right leg. So now it will become easier to do the analysis if we sort of abide by some conventions, just so that it's that our description of the robot and the kinematic chains is consistent. So a chain with n joints usually has n plus 1 links. If we look at the humanoid robot and our Thormang, then you can see there's one motor here for the left arm. We have one motor here. Then we have, so let's put the origin of our robot, of our world coordinate system in the torso. Then we have the move from the torso to there. Then we have one joint. Then from here we have a link that goes to this joint, second joint. Then from there we go to this motor here, our third joint, and then our fourth joint, and then just ignore the gripper for now. We'll just assume this is one finger that doesn't actuate. So we have 1, 2, 3, 4 motors, 4 joints, but I have one link from here to there. Then from this motor to this motor, 2, 3, 4, 5 links. Right? So we have 4 motors, 1, 2, 3, 4, and I have 5 links. So we, by convention, we label the joints from 1 to n and the links from 0 to n. In theory, we don't have to do that, but it makes things a lot easier when you reason about them. Also, we want to be systematic in the way that we assign our indices. So for example, here on the Thormang robot, Of course, I could call this joint 22, and this is joint 9, and this is joint 3, and this is joint 7, but that doesn't make a lot of sense, right? There's no point to use a indexing scheme like that. Instead, as we move along the chain, we label the joints. So this would be joint 1, joint 2, joint 3, joint 4 here. So joint 1, joint 2, joint 3, joint 4. And that's our labeling that we use. Then this would be like 1 left, 2 left, 3 left, 4 left, and this will be 1 right, 2 right, because it's a different kinematic chain, right? The right arm doesn't influence the position of the left arm at all, so the two are going to be dealt with independently. We don't try and deal with them in one set. They belong to different kinematic chains. So from the root, we assigned joint coordinates in increasing order and ascending order, which means that then joint K will connect link K minus 1 to K, to link K. Joint K does not affect the position of links 0 to K minus 1. But joint K does affect the position of the links from K all the way up to N. Each joint has a joint variable which is its control, which is what we can actually modify. Let's see how to modify the color. HTML5 color, text color. Oh, color, not text color. So this is an important concept, and we also allow it to act as sort of generalization. So the joint variables are usually indicated by Q. So theta I if it's a revolute joint. Di if it's a prismatic joint. Now in order to control the joint, I need to assign a coordinate frame so that I can specify what that control is. If I rotate it, I need to have a coordinate frame and I need to say in which axis does this rotate, x, y, or z of that particular coordinate frame. If it's a displacement, then I need to specify the direction of the translation. So we need to attach a coordinate frame to each link, and that one has origin I, OI with axis XI, YI, and ZI. Now, given the way that we assigned these coordinates, that means that the coordinates on link I are constant in the coordinate frame OI. Because if that link moves through joint control I, then the coordinate frame is also going to change. So the coordinate frame that we attach, it has to respond to our control. So, for example, if I have an elbow, and let me get it in the image, and now I want to have the coordinate x along the direction of the elbow. Now if I rotate, then the coordinate frame has to rotate as well. Now one frame is special, frame 0. Is called the inertial frame. You can sort of think of that, or that would correspond to our world coordinates of the robot, the position of the robot in the world coordinate system. And this is sort of where the drawing really comes in handy, because when you're dealing with coordinate frames like that, then you try to think about it. It's really hard to visualize things in 3D. So then you end up and say, oh, this is my x coordinate system, x, y, and z, for example, rotating this way. Now I have another coordinate system, but then the left hand doesn't work because it's a left-handed coordinate system then. So then you need to remap it, need to think about what happens to x, y, and z as you rotate this shape. It becomes very complicated. Then people usually start using pens in order to try and model so they have a red pen for the x-axis and a y pen, a green pen, and a blue pen. But if you have more than two, that becomes very complex very quickly. So as an exercise and an example, let's draw. Let's not. Yeah, let's not draw right now, but keep moving. Now, homogeneous transformation matrices are important because, as we saw, they allow us to model all the effects that the robot joints have on the robot. We only have revolute joints, so that's a rotation. We have prismatic joints, that's a translation. And both of those I can model using homogeneous transformation matrices. So in this case, for a humanoid robot, we have to deal with 4x4 matrices, and then we define the homogeneous transformation matrices as the effect of joint I on link I plus 1, I plus 2, I plus 3, so on and so forth, the other links in the chain. See if that works in RST. Don't think so. So the coordinate frames from OI minus 1 to OI can be connected by a homogeneous transformation matrix. Let's call that matrix AI. A describes the position of OI with respect to OI minus 1 the transformation matrix depends on the joint variable Qi. Because I can change it, so then the actual displacement, the change from link OI minus 1 to OI, that will be changed because now the rotation is different or the translation is different. So AI is a function of Qi. However, right now that just means that for each one of my motors here, I have matrix A1, A2, A3, A4, right? But they are only the relationship between the previous link to the next link. So A4 will only model the transformation from link 3 to link 4 to the end effector there, for example. So that's not sufficient, right? Because if I want to know the position of the end effector, then that depends not just on this joint, but also on the previous one and this one and this one. So we define transformation matrix T from I to J So if I is less than j, then the transformation matrix is a I plus 1 multiplied by a I plus 2 so on and so forth, up to a j minus 1 multiplied by a j. So to go from link I to j, we multiply the matrices, but as you can see, we right multiply them. So I'll explain a little bit why we right multiply them rather than when we were dealing with homogeneous coordinates, we actually had to left multiply them. So from I to j is equal to the identity matrix if I is equal to j and t oh here. So let's have a look and see why we right multiply the matrices. So if we take the points and then we translate them with T and then rotate, with rotation matrix R1, and then translate again with T2, then the compound transformation matrix is given by T1 and left multiplying. So T1, R1, T2. But what they ask us to do for the kinematics is we're supposed to calculate T1 multiplied by R1 multiplied by T2. So we're supposed to right multiply. So why do we do that? For that, let me go back to not this one, but our homogeneous coordinate from yesterday in 2D. And let's just add a little bit to it. Then remember yesterday when we were playing around with the arrow in 2D. And then derive the translation and rotation matrices in 2D. And then here we said that rotation after translation gives us the light blue, translation after rotation gives us the yellow. So the two of them are not the same, so we have to be careful. And in this context, the correct answer is that you must left multiply them. Even with the robots and the kinematics, we are actually left multiplying it, but the difference is that we have to be careful about the point that we rotate things around. Some more arrow figures. So far, the rotation is always around the origin. Right? If you look at the figure here, when I rotate the point, this is the rotation, this is the origin, 0, 0, right? 0, 0. Then the shape will rotate around this point. However, if I want to rotate around an arbitrary point, then how can we do that? Let's do that here, where our arrow is. So let's rotate around the tip of the arrow. The tip of the arrow would have coordinates 0.25 and 4. Zero point 0.5 and 4. So if I want to rotate around that point, then what I have to do is first we have to translate the point XR, YR to the origin. Or move the point XR, YR so that it maps the origin. Then rotate by theta, and then move point back to move the whole thing back to XR, YR. So this would be translation by minus XR minus YR this would be rotate theta, and this would be translate XR, YR. So first we move XR to the origin, so that we need to translate the whole thing by minus XR minus YR. Now point XR, YR is going to be origin, then rotate, then move the whole thing back to XR and YR. So XR, YR are equal to 0.5 and 4. Then my transformation matrix, the cumulative effect is going to be minus XR minus YR then rotate by, let's say, 70 degrees. And then I have to translate the whole thing back to XR, YR. We can apply that. This would be our transformation. we rotate that. So here's our figure now. You can see this is rotation around the origin. This is rotation around the point 0.54. That gives us the green one here. And this is achieved by exactly this line of code here, where first we need to translate minus XR minus YR, then rotate, and then translate it back. Okay. Maybe a little bit too big. So now let's have a look and see what happens if we do this with in the context of kinematics, where we're following along a kinematic chain. In that case, what we want to move is we want to move the coordinate system. Right? We move it to the first joint, then we rotate it at that point, then we move in order to align it. Then we move it to the next joint, we rotate around there, around that point, in order to align it. So here we move first to the shoulder, then align the coordinate system here. Then from here we move to there, then rotate the coordinate system, but the coordinate system that we want to align it, so it shouldn't be rotated around the origin, it should be rotated around its current position. So we translate the coordinate frame to the joint position, and then we rotate it to align it with the link. And I'll talk some more about exactly how this alignment works. But that means that we want to rotate around the position of the joint to align with the link, not the origin So assume that we have a joint position x1, y1, z1. Then first xi, yi, zi. So we translate to the joint position T then rotate around position zi by angle theta. And then we have to translate no, that's what we want to model. So first translation, then the rotation. Right? But if we break down rotation around a point, and I call this translation here T1, call that T translation T1. Then we need to rotate around this point by angle theta, point into its three components. Then what do we have to do? So let's call this our rotate by theta. Call this R2. Then the compound The rotation here is by theta, but not around the origin, but by x, y, z, I. So maybe call that rotate. Rotate point. If we have R2, then I get compound transformation is first the translation, T1, and then the rotation, R1 multiplied by T1. Right? First translation, then rotation, left multiply, the usual way, the correct way. But now if we break down the rotation R2 into its components, then what we need to do is move from the joint position xi to T2. We need to move from that point to the origin. So I need to apply the transformation like this, which means it's equal to then we need to rotate round origin. T3, 4. So this is around the point. So no x, y, and z, I parameters. And then I have to bring it from there back to the position. And I just label them 1, 2, 3, 4, even though they're different styles like R and T. Just to make the, I could replace all the A's and R's and T's with A's, but I think that will make it more confusing. So that means that the compound transformation is now this part here, right? So it would be T2, no, T3, and then rotation by theta, so that I labeled R4, and then a translation back T5. So now the R2, R1, it should be R2, R2 I now replaced with T3 followed by R4 followed by T5, right? Again left multiply. But now when you think about it, T1 and T3 are inverse of each other. So T3, T1 followed by T3 is the identity matrix. So then we end up with the transformation is T, and this is not T5, this is the same as T1 here. Right, so T1 and T3 are inverse operations, so T3 multiplied by T1 is going to be the identity matrix, so I end up with T1 multiplied by R4, not R2, for the rotation around the origin, not the rotation around the point. So now that looks right multiplied. We do translation first, then rotation. But we do rotation first, then translation. But in fact, yes, it's going to work out correctly because our point of rotation is not the point of origin, it's the point at where we positioned the joint. So we end up with, even though we're doing translation first, then rotation, it's the rotation around the point, this is a rotation around the origin. But they end up working out to be correct in both, in this scenario. So that's why when you look at the transformation matrices here, we are right multiplying. So these A's are all R's and T's, and we're just ending up right multiplying our matrices. So now based on this, we can define the end effector position. So let O from 0 to N be the position of the end effect. That's what we really want, right? That's the position of the end effector in this case the hand, in the inertial frame, in the world coordinate system. So that is going to be defined by a homogeneous transformation matrix, which has two components. One is the rotation matrix from 0 to n, that relates the axis of the end effector and the inertial frame. Then we can define H as the homogeneous transformation matrix from the inertial frame to the end effector. So R0n is a 3x3 rotation matrix. So ON is a 3x1 vector, and R is a 3x3 matrix. So this H is the cumulative effect of all the transformations. So that's H is the transformation from 0 to n, which is the right multiplied sequence of transformation matrices. So A1, Q1, multiplied A2, Q2, up to AN, QN. Now each one of those matrices, AI, QI, consists of is the 4x4 matrix, which is its component is the mapping from R I-1 to I given QI, and the displacement from O I-1 to I given QI, and 0 and 1. So this 0 here actually corresponds to a 3 by 1, a 1 by 3 vector. This should be 0, 0, 0, 3 zeros, and then 1, 1. It's just to match up with the 3 by 3 matrix here. So transformation from I to J is equal to A I plus 1 C dot A J which is equal to the rotation matrix from I to J given the various matrices, and O from I to J with all the variables now for QI plus 1, QI plus 2, QI plus 3, all the way up to QJ. So this is our definition of the homogeneous transformation matrix to model the position of the end effector with respect to the world frame, right? So this H is what we're interested in. So the rotation matrix R IJ shows the relative orientation of link I to J It's a 3 by 3 matrix, and in fact it's orthonormal as well. We can scale it so the norm of the column and row vector should be 1, and then it's also orthonormal, which means that if I transpose it, I get the inverse matrix. So it has some constraints on it. It's just not. It's not just any any 9 numbers that will form a rotation matrix. So this comes from the rotational components of the homogeneous transformation matrices. So R I to J is given by R I to I plus 1 multiplied by R I plus 1 to I plus 2 all the way up to R J minus 1 to J. The coordinate vectors are defined recursively O from I to J is equal to O from J minus 1 to I plus, and now I need to rotate them. J minus 1 multiplied by O J minus 1 to J. So the important thing to realize is that the rotation is important. Our displacement of the origins is not all given in world coordinate systems, but as actually is in the local coordinate system, which is why when I need to when I add them up, I need to look at the current alignment between link I and j minus 1. And then apply the transformation matrix. And that's the solution or the framework for calculating the solution to the rotation, to the forward kinematics problem. In theory now I could solve it, right? I could say if I have given joint coordinates theta 1, theta 2, theta 3, then I can, and I have these, I can calculate these rotation matrices and the transformations with the origins. Then I can calculate the end effector position. All that is required is to find this H matrix. However, that is possible, but it's not a very elegant, very smart way to go about it. And next class we will look at the Danavid-Hartenberg convention, which allows us to simplify the assignment of these coordinate frames. Like in theory now I can place coordinate frames anywhere I want. So for this particular robot I may place O1 here and O2 there and O3 there. And that would be possible, but it wouldn't make a lot of sense. It wouldn't help me in understanding the motion of the robot. So we usually constrain ourselves to a convention, to the Danavid-Hartenberg convention, which greatly simplifies and allows us to come up with an alignment of coordinate frames that makes sense, that intuitively makes sense as well. Like it seems like a good way. It's not a burden, it's not an extra constraint, but it actually helps. You would most likely choose these positions for the coordinate frames anyway, even if you were given completely free choice. Because, for example, to model the translation and transformation from this joint to this joint, then usually you would want to have the coordinate systems attached to the joint here, to the motor somewhere, not out in free space somewhere here, somewhere there, even though that's possible. That wouldn't help you in understanding the motions. The coordinate systems that we use here, right, those are all arbitrary. The only thing that matters is from the world coordinate system, can I calculate the position of the end effector? What these coordinate numbers are with respect to this joint or that joint or that joint doesn't really matter as long as I end up with the correct real world coordinates for my end effector. Okay, good. So that's it for this class. Our next class, I would like to run it tonight at 6 p.m. and then we will talk about the Danavid-Hartenberg convention. So we'll run one class tonight at 6 p.m. And then there will be no class on Sunday. Bye bye, have a rest.